As is usual for this month of September, our sponsor is Tacoma Strategies. And our speaker today is Herman Dorland, who holds a PhD in geology from the University of Johannesburg. During his PhD, he worked on regional correlations of sedimentary successions on the Karpval Craton using paleomagnetic analysis and zircon geochronology. Following the completion of his PhD in 2004, he spent a year working as a postdoc researcher at the University of Ottawa. He then joined Anglo Coal, where he worked first logging core and later as a geological modeler. In 2012, he joined Snowden, working mostly for reviews of banks of coal projects. From 2015 to 2018, he worked as a research associate at the University of Johannesburg. Afterwards, he started his own company, developing software for geometallurgy and performing projects. Today, Herman is talking to us from Bogota in Colombia. It's 6 o'clock in the morning there. The presentation that Herman is going to be talking to us about is sampling, multiple crush experiment variability, a new way to quantify the nugget effect, and how resource estimates changes if you change the drill plan. Sounds like a really interesting presentation, Herman. We look forward to hearing from you. Everybody else, please make sure your videos and mics are off, and we'll take questions at the end. Thank you. Herman, we look forward to it.
Thank you, Tanya, for the kind introduction. Good morning, everyone. Yes, in the mining industry, usually when we take a sample, we take a drill core sample. We then take it to the laboratory where it's crushed, milled, and then it's a very small sample is taken. Often it's about 2 grams out of the 10 or 15 kilogram sample, which is then analyzed for whatever variable you're looking at. In gold, it can be the concentration of gold, or in coal, it can be the CV or the ash. But it's only one sample that's taken from the lot of the drill core sample. So if you could take a small sample from the lot over and over and analyze it, you wouldn't just get one value for your variables that you're analyzing for, but you would get eventually a distribution of values. And it can say for the gold example, it can vary between 2 and 10 or 2 and 15 grams per ton. So then, depending on what sample you took first, that's usually the case. Is the first sample is taken as the actual value of the sample. Then you can underestimate the resource if it was 2 grams per ton, and overestimate it if it was on the other side, if it was 15 grams per ton. And this we don't know from normal sampling. We don't know the distribution of the values. We only know of one sample, and we're assuming the distribution is, you're assuming that you're taking a representative sample the first time you do the sampling and analysis. So what is a representative sample? A representative sample is a subset of a population that seeks to accurately reflect the characteristics of the larger group. So if you had 30 students in a room, 15 males and 15 females, you could generate a representative sample that might include 6 students, 3 males and 3 females. So representative samples are all about proportionality. So you keep the proportions of the population in your sample. So today, my outline of my talk is I'm going to talk about sampling errors, then I'm going to talk about multiple sampling experiment variability, then about multiple crush experiment variability, and then some conclusions. First, sampling error. The correct sampling error is the first one we'll look at. For example, the fundamental sampling error is a function of the constitutional heterogeneity of the components making up the lot. So it's inherent to the sample. It's also grouping and segregation error due to the distributional heterogeneity of the lot, or the way the components are distributed before you sample the material. And correct sampling errors cannot be removed. It's inherent to the material. However, thinking about correct sampling error is deterministic at the moment. You take only one sample per lot, so you don't know the distribution if you would analyze it, if you would resample it over and over and analyze it. So some incorrect sampling errors, delimation error, if you don't sample through, delimit the sample very well, extraction error, contamination error where you add material to the sample loss where you lose material in transfer, alteration, chemical and physical alteration. And then you can also have something like sample swap where you set sample B as sample A and sample A as sample B in the lab. These errors can be, you can improve your this error. It's not inherent to the sample. So if you have better practices, you can improve this. So multiple sampling experiment variability. Say you have a lot consisting of a certain amount of red, green, orange, blue, pink and gray particles, and then you mix it well, and then you sample it. In this case, we sampled every time in column 5, and each time of all the experiments you take, you get a different answer to what is in the lot. So from the sample you're taking, although it's well mixed, you always get a different answer. This is something that is in statistics called resampling. So you sample many times over and over, and it's well known in statistics, and it's to get a distribution of what the sample might look like. So if you look at the orange particles, we see in the first experiment we got 4 in the sample, in the second 1, and then in the third 2, in the fourth 2, in the fifth 1, in the sixth 4. But the representative sample was 2. So we often, although we sample, we don't get the representative sample. We get something else when we get a maximum and a minimum. Of a maximum of 4 and a minimum of 1, for example. So we don't get the representative sample when we sample, even if the material is well mixed. This is just the diagram of what happens when we average these are the 6 experiments. And then this is the average, and this is the proportional representative sample. So for the individual sampling experiments, we never get what the representative sample is. When we average out the 6 experiments, we are we're starting to approach the representative sample constituents. So this is what the sample values really look like. It is not single values, but the distribution. For example, we know now that it could be a weight percent of gold or grams per ton. We know with 99% confidence that the value for the sample is between 0.5 and 3.5. So at the low value, we could analyze and we could get a sample that gives us 0.5 grams per ton, for example, and this would underestimate the resource if we do resource estimation with that. On the other hand, we could have taken a sample of 3.5 grams per ton, and we would overestimate the resource, and it's very improbable that we would actually get the average of the average sample, the average value for the sample from sampling one small sample per lot in the drill core. So this is just another way of looking at it. In the sketch, we have 15 particles. It's where the rock was broken into 15 particles. We have gold grains in some of the particles, and the rest is just gangue minerals. So we know that the average grade is 5.33 grams per gold. That's just an example of is the grade per ton. We then start taking samples. We take 3 samples from 15 samples together, the small 3 particles from 15 particles. We just get a small sample from the lot. there's 450 ways to take free samples, free particles from 15 particles, if order doesn't matter. Out of the 450 ways to take these free particles, there's say 10 ways in which the average grade can be made. So then the probability that the average grade sample is selected is 10 over 455. That's about 2%. So the probability is very low that you will obtain a average grade or a proportional sample from the lot, with sampling the first sample that you analyze. So that's another way of looking at proportionality. This is a sample with metal particles in it and also gangue minerals. This blue line underestimates the metal particles, the red line overestimates the metal particles, and the green is a proportional representative sample. So it's very unlikely that you will get the sample with this that is indicated by this green line by crushing and milling and sampling. So then just a discussion on multiple sampling experiment variability. It's related to correct sampling error. The value of the representative sample cannot be known from physical sampling. The amount of resampling to make bootstrapping estimates is impractical to achieve with physical sampling and analysis. So you cannot really do resampling, analyzing the sample 1,000 times over with physical methods, and we just don't know what is the value of the lot because we are obtaining samples, so we don't know what. So we cannot we don't know what is the value of the representative sample. It is highly improbable that the sample obtained through physical sample is not representative. And because the representative sample is unknown, it cannot be known if a representative sample was obtained. So we won't be able to identify if we have a representative sample. Grade for a sample varies as particles are mixed and sampled over and over. This can be simulated using a computer for slices of ore, using quantitative mapping, virtual crushing and sampling, or bootstrapping resampling. Variability changes with the size of the particles as well. So the confidence or intervals are particle size dependent. Sampling and physical and the analytical outcome is therefore probabilistic by nature. It is incorrect to use a single deterministic analytical outcome as the only value a sample can be for which the average representative sample is unknown. And for that duplicate is also not enough to know the true value of samples. It's almost similar to taking one sample per lot in the drill core. Resource estimations should therefore be based on distributions of many outcomes and a single analysis not taken as the only truth. And in this, it's very important to characterize the ore that you're working with, because the size and distribution of ore components determine how accurate the resource can be estimated or how easy it is to obtain a representative sample from the lot. We're now going to look at that a little bit. So this is just a way to look at the nugget effect. This yellow spots are metal grains or gold grains in the gray, that's gangue minerals. All of these scenarios are 20 grams per ton metal, so they all have the same average metal grade. But if you look at the distribution of the components in the gangue, this is 100 micron, for example. This is very finely distributed. So per gold grain, you have very little waste material. So it's easy to obtain a representative sample from a small drill core in this case. However, if we go to the other extreme, we can have 21 tons of waste material per gold grain. So you cannot obtain with a small drill core sample, you cannot obtain a representative sample in this case. So ore characterization is very important to understand how accurate the resource can be estimated, or how good is your your representative sampling. So it's just an example. If we look at the first case where we have very little waste material per gold grains, it's easy to obtain a representative sample from drill core. And if you have a very large amount of waste material per metal grain, then it's impossible to obtain a representative sample using drill core, a small sample that you take. This is a photo of a gold ore. This was a drill hole drilled. It was 7.5 meters at 2.9 grams per ton with a speck of visible gold. And when they mined it, eventually, it was 3,500 ounces of gold and 7 tons of quartz. So this drill core almost completely missed the mineralization that was present. So this is just an example to show that your drill pattern really matters when you are estimating resources. So we could have a resource, a deposit, and we could drill holes in it. And we could, with 3 holes, we could hit the mineralization each time, and it's 30 grams per ton in all the holes. So then we would estimate the resource, and we would get a grade of the lot to be 30 grams per ton, but we know that the average grade is actually 15 grams per ton if we included the waste material. In the second drill pattern, it was just a little bit different in the first one. We drill into waste twice and we get 0 grams per ton in those holes, and once into a 30 grams per ton hole. And then the average grade of the drill pattern, the estimate would give a resource estimate of 5 grams per ton. But we know that the grade of the lot was 15 grams per ton, so we would underestimate with this drill pattern. Now I'm going to talk about multiple crush experiment variability. This is a piece of coal. We have vitrinite, as the gray is black and the yellow is mineral matter. This is on the left is a coking coal particle. It's got 90% vitrinite and 10% mineral matter. So we then crush this piece of coal as the red lines are shown, and this little M's are standing for millings particles. So we are making no product at this crush size, and this is also indicated in the washability table, where we just have milling particles. We then take the same chunk of coal and we crush it a bit finer. We start making product particles, but still a lot of it is just milling particles where the coking coal product is not liberated. And this is again, you see the yield in the low density is changing. So we are making, at least we're making product particles now and product. We then crush it the first crush size, third crush size, and then we're starting to make a lot of product particles, again some milling particles and also some zinc particles. So again, by crushing finer, we are increasing the product yield in this coal. However, this is not always the case. We can have a parent particle and we can then crush it finer, but the density of the parent particle of the daughter particles are exactly the same as the density of the parent particle. We then crush finer, and we again make the same density as the parent particle, 1.7 RD, and we can even crush finer, and we still have the same density. We don't liberate the product. We're still making millings particles, and this is called the mini-me effect. The mini-me effect can be even on micron scale. This gray is purple material. This is mineral grains. The yellow gray is the macerals in a coal. So to liberate the mineral matter from the macerals, in this case, we will have to crush to less than 10 micron or so, and this is impractical. So then we know we cannot upgrade this coal, so we will have to use it as is. So another example from coal, we have vitrinite and mineral matter plus vitrinite. So to liberate these vitrinite laminations from the mineral matter plus vitrinite, we'll have to crush to 20 micron, and again, this is impractical. So the mini-me effect can be at very small scales. So from the sketch example, when we look at the coal washability, it's not just one single value. It depends on the size of the particles, and there's several distributions of washability elements that makes up the total washability of a sample. In the large particles, we'd have less yield for your product, and in the medium and small particles. It's also market specific. If the market will take the small particles, then we can have better yields and make more revenue. However, oftenly the market only takes large particles, and then we're analyzing our borers in the small particle area, and we then process it in the large particle area. So it's very difficult to do reconciliation in this example, and we always get something different than what we estimated. This is a sketch. These round spots are knowns, and the crosses are unknowns. So it's just to show that the unknown is actually the distribution of values, and it's not a single value that you're estimating. So when you do resource estimation with washability, you must specify the particle size. Otherwise, it doesn't make that much sense. This is an example from an oolitic iron ore. This is a scale of 1 millimeter to show the scale. So it's about 4 micron per pixel resolution in a scanner from an office scanner. We scan the image, we then classify it using artificial intelligence software, and we get all minerals and quartz. In this example, the material is then broken into -2 millimeter particle breakage pattern. At this size, we don't liberate the quartz from the iron ore minerals, and we just make millings particles, so we don't obtain product. However, if we break the 0.1 millimeter particles, we obtain a lot of ore mineral liberation of goethite and hematite, and we separate it from the quartz, so we get good liberation. So the washability changes with size. And this is just if you do 5 simulations of the 0.1 millimeter, all the simulations almost fall directly on top of each other. So in this case, the breakage patterns doesn't really matter that much. About the washability doesn't depend on breakage pattern. In this example, if we were analyzing a bulk sample, there would be high predictability of plant outcomes from the bulk sample. However, if we were analyzing a 2 millimeters, look for example at a density of 4.6 grams per cubic centimeter, the yield varies between 35 and 70%. So there's not much predictability at this size. So even if you had a big bulk sample, it would give a poor indication of what would happen in the plant if you're going to process at this size. So it's the summary diagram of this is particle size for the oolitic iron sand. This is weight percent for the 5% SiO2 product. At small particle sizes, at large particle sizes, there's a lot of variability for the sample. It varies between 0 and about 55%. So it's very unpredictable. Then if you break to 1 millimeter, the variability is a lot less. It's between about 47 and 55. And then the yield at 0.5 millimeters, the yield increases to about 92% from 45. And there's very little variability between the washabilities. It's about 92 to 95%, 5% SiO2 products in all the simulations. So what happens if we crush finer to the variograms? The range is very short for the big particles. While if we crush finer, the range increases a lot, and the predictability of a distance increases. And this is often what happens is that we are analyzing our cores in small sizes, and then we are processing at large sizes. The the predictability changes, so we won't get what we had in the resource estimates for the small sizes. Just a discussion on multiple class experiment variability is related to the correct sampling error. The average representative washability cannot be known because washability is infinite. We talked about this in a previous talk. Liberation and washability take on a range of values with different breakage patterns. At small sizes where components are better liberated, breakage patterns play a significantly smaller role in predicting washability than at larger particle sizes, and washability can be more accurately predicted. And then resource continuity, product in the resource, plant performance, and reconciliation are all influenced by multiple class experiment variability. So in conclusion, it's highly improbable that the average grade sample is obtained using physical sampling methods due to multiple sampling experiment variability. And this has an impact on all resource estimations. Different breakage patterns of the same sample give different liberation and washability outcomes. The type of ore influences how accurate the resource estimation can be made. So ore characterization is very important in resource estimation. And it's not often done that well if one look at competent purchase reports, for example. Drill pattern influences the resource estimation. Due to multiple sampling experiment variability and multiple class experiment variability, even bulk samples can give highly unreliable results about the ore. So it depends on your component distribution and size. Simulation can provide more accurate information than physical tests about grade and washability of samples in many instances. This is a sketch I call Patience. It's just a final thought on this. I think we can look at sampling in a different way using computer simulation and artificial intelligence, and it will become more clear in future how we can use computers in analyzing samples to obtain better and more accurate resource estimates, and also to predict how the business is going to perform in the process plant and so forth. Thank you for listening.
Thank you very much, Herman. Okay, folks, we will take some questions if anybody has. Just raise your digital hand.
Good day. Sorry, I don't know how to raise the digital hand, but can I ask a question?
Go ahead, Rob. Answer your question.
Hi, thanks very much for the talk. One sort of question I've had for some time actually is when resource estimations are actually reported on, they're given as set figures. I've long thought that, like in JORC, I don't know what it's like in the actual SAMREC code, but when you do the exploration target, you give ranges. And I'd like to know, based with your sort of discussion today, to me it emphasizes the fact that you cannot give single sets of data. For instance, graphite, where I've got some experience, I've seen many reports where they actually report the resource down to single figures. In other words, 20,443,254 tons at a set grade, which is sometimes quoted to 2 decimal places, 5.43% graphite. I'd much prefer to see a range. Could I ask your comment on that, please?
Yes, I think, yeah, it's with physical sampling and analysis, it's not possible to, I mean, you just take one sample and analyze one sample, and then that is now you hope that it's a representative sample, but it's a very poor assumption that it's representative. So it's value. You must quote, perhaps with simulation, you can analyze by resampling, with computer simulation and image analysis, you can actually simulate resampling. So you can simulate resampling for 10,000 experiments or whatever, and then get the distribution of the sample values, and then yeah, you get a range of values. You don't get a fix. Yeah, it's not. You cannot just get one specific fixed value for your resource. And with liberation and washability, it's even more like that. Depending on the particle size of the breakage that you get different values. So you cannot. Yeah, you have to report at the size you're going to process it. So if that answers sort of the question.
Partly, yes. I was interested in, there was one talk I listened to where they had a petroleum geologist who came on and said, look, in that industry, they look at a range of resource estimations from a low sort of confidence to a high confidence. And what they actually end up quoting is the lower confidence figure, because he said what the investment industry wants there is to know for sure what's there. Okay, now look, we're not talking about gold, which is a much more complex thing with its sort of, with its nugget value. Look, it won't happen, I'm sure, but I would much prefer to see ranges given when people quote resources, both in terms of tonnages and in terms of grades. Now, with a thing like graphite, it's a bit less affected by the nugget effect, let's call it that. But nevertheless, there are these very, there are the sampling errors that come in. So look, it's just a point that I'd like to make, that I am highly critical of the way that both in JORC and as far as I understand it, SAMRAC, single figures are only quoted, which I think is very wrong. So that's more a point than a question. Thanks.
Okay.
Well, that's a discussion that can go on for many hours. I look forward to engaging you on that at some stage.
Okay.
Carol, would you like to ask your question, please?
Yeah, my question is more to do with software, whether Herman can recommend some watchability software on the market out there that we can do.
Sorry, Carol, can you go closer to the microphone? We didn't hear you.
I'm saying, I'm just wondering if Dr. Dorland can recommend software on the market we can use for watchability curves and things like that, using Paul especially.
Sorry, can someone just to repeat the question if you could have if you heard it?
Carol, your microphone's not working so well. Would you like to type that question in on the chat line, and then we'll be able to ask Herman?
Where's my software for is going to.
Does anybody else have a question in the meantime while we wait?
Ah, and I can't get out of this guy's chat. How can I do that?
Let me show you.
Wait.
Go back.
Unmute.
Mom, just go back to chat. You there? Just take it there and then say to everyone.
That's fine. If you stay that distance from your microphone, that seems to be working nicely. Try and ask your question again.
All right. My question to Dr. Dorland for everyone is that when he recommends softwares on the market for watchability curves, or softwares especially for core, people seem to be struggling with that.
No, we're still losing you.
Well, you sent the question.
Control copy. I sent the question.
Okay. Okay, Herman, the question from Carol is, could you recommend software for washabilities?
No, I'm a bit biased in this because with virtual geometry, we developed a software that we can simulate washability with. It basically works on the principle that you scan the piece of material you're working with, like the iron ore, with a normal office scanner. So it's quite cheap to do that. You just cut the surface, scan it, and then you train the software to map the specific components in the piece of sample that you scanned, and then you can virtually break the material into different particle sizes using the software into different virtual particles, and then you can get washabilities for any size that you would like. So you can analyze it at 1 centimeter particle sizes, or at 15 centimeter particle sizes, or at 1 millimeter particle sizes. So you can analyze for the same sample for any different sample size, particle size. So yeah, we have that software that's basically ready to, we translate it into Python, and it's basically ready to be run from the web where people can use it. But we are still in testing phase. It's probably going to take another few months to just test it. But the MATLAB version is basically, we've been running it for more than 2 years now. So
Thank you. Anybody else with a comment, question? Or are you all, like myself, very worried now about my sampling program?
Very worried.
Yes. Herman, thank you so much for taking time out of your very early morning to come talk to us. We really appreciate it and look forward to the next in the series of these presentations. Hopefully you'll be able to tell me that my sampling is getting better or getting easier. It looks like we have it's the question. Herman, thank you very much. And thank you all, everybody, for being with us this afternoon. And we look forward to seeing you again at the next lunchtime lecture. Thank you. Goodbye.
thank you, Tanya. Bye.
Thanks so much, Herman.
Thank you, Nalin. Bye.
Take care. Chat soon. Bye.